We begin this unit on radicals by looking at square roots. The hope is that these first couple lessons are easier than what we've been doing in class, working with rationals and fractions, but they will build towards concepts that are definitely a little more difficult. So the goal here is to understand basic square roots and build towards how to break square roots down in a way that then we're going to be able to eventually combine different roots and do problems involving variable roots. So initially it might seem like it's super easy, but basically as long as you know where to find things in the calculator in this unit, or in this section I should say, the real difficult part I would say is dealing with variables, but even that shouldn't be that bad. So where we're going to start with square roots is finding square roots of perfect squares. Then we're going to look at finding square roots using the calculator, and finally how they are adapted for variables. So addition and subtraction, reverse operations, so multiplication and division. Here we're going to talk about the reverse operations that are raising a number to a power and finding the root of that number. So for instance, the square of 5 is 25 because 5 times itself, or 5 squared, equals 25. The square of negative 5 is also 25 because negative 5 times itself, or negative 5 squared, equals 25. So really, whenever we want to find what number squared is equal to 25, there'd be two possible answers. We would have both the positive answer 5 and the negative answer negative 5. So in general, we have the following definition. Number b is a square root of a if b squared equals a. Every positive number has two square roots, one positive and one negative. Two square roots of 9 are plus and minus 3. Two square roots of 144 are plus and minus 12. The number 0 is the only one that doesn't have a plus or minus because the concept of 0 is neither negative or positive. So really when I do 0 squared, I just get 0, but that's the only square root is 0. The radical symbol represents the positive or principal square root of a number. So even though it's true that the general idea of a root gets you to plus or minus, when you see the root symbol, you can assume they want the positive root, unless they put a negative in front of the root symbol. So for instance, when I see just the root of 9, the answer is positive 3, even though plus or minus 3 would get you to 9. As opposed to if there's a negative sign outside the root symbol, that tells you they're really looking for the negative version of the root. So the negative of the root of 144 is negative 12. So basically, if you just see a root, assume the answer needs to be positive. If there's a negative outside, that changes the sign of the answer. If a is a positive real number, the root of a represents the positive or principal square root. Negative the root of a represents the negative square root. Just for general terminology here, the radical symbol is this square root symbol here. The radical is the whole thing, and the radicand is the thing that you're taking the root of inside of the square root symbol. An algebraic expression containing a radical is called a radical expression. Some examples of radical expressions are root of 100, root 2 plus 3, root x squared, and root a minus 1 over 49. What these all have in common is some element is under the square root, even if there's parts that are not under the square root. Find each square root. In each of these cases, these are perfect square roots where we can just say what times itself equals this. That said, even though all these questions say do these problems in your head or try and figure this out without using a calculator, use a calculator if you have to. It does not bother me. It would be great if you memorized all these squares. We do have your page of perfect squares and cubes, which is available to print at the top of this unit. But basically, if you're using a calculator here, I'm fine with you using a calculator here as well. That said, they're going to go through how they come to their answers. If they're looking for the root of 16, they get 4 because they tell themselves 4 times 4 is how you get to 16. Same idea with 1. 1 times itself equals 1, so it is the square root. Little harder to see how 0.36 comes together. It is 0.6 times 0.6, But this is the type of thing I would just throw it in the calculator instead of trying to figure it out in your head. For the root of 4/9, basically you can split that up into root of 4 on top, root of 9 on bottom. So the root of 4 is 2, the root of 9 is 3. That's how I wind up with 2 over 3. Negative the root of 225 is the opposite of the root of 225. The root of 225 is 15, so it becomes negative 15. Square roots of certain numbers, such as 7, are hard to compute by hand. We can approximate it with a calculator. So here's 3 square roots that we can do in our head, or if you want to use a calculator for it, you could. What times itself gives me 49? 7 times itself. So the root of 49 is positive 7. What times itself gives me 100? 10 times itself, so the root of 100 is positive 10. Here, what times itself gives me 1? The answer is 1, but then the negative outside makes me give the negative answer of negative 1. So when we approximate irrational square roots, to find the principal square root of 7, we enter it into a calculator. We get the approximate square root is 2.6457513. In general, they ask you to round to 3 decimal places in Cengage. So what that would mean is after the decimal, I move 1, 2, 3 places. I want to round to this spot where the 5 currently is. I look to the right of the 5. If the number to the right of the 5 is 4 or less, I just drop it and leave my answer as 2.645. But in this case, because the number to the right of 5 is 7, which is 5 or larger, it means I bump this number up 1. So my response would be 2.646 after rounding to the 3rd decimal place. So here this is showing rounded to 1 decimal place. If we tried to do 2.6, that would only get us to 6.76. 2 decimal places, it would end up being a little more than 7 when we squared it back. 3 decimal places, it gets really close to 7. There's still this little bit that it's too much, but this is why in general they tell you to round to 3 decimal places on these. Whole numbers such as 4, 9, 16, and 49 are called integer squares because each one is the square of an integer. The square root of an integer square is an integer and therefore a rational number. So when I get a whole number answer from any of these roots, the answer is rational. As opposed to, if I take a square root that isn't a whole number, I get an irrational number, and it's irrational because really I can't represent it with a simple fraction. So recall the set of rational numbers and the set of irrational numbers together make up the set of real numbers. Here we're going to be looking at how to find each of these numbers and round it to 3 decimal places. So the only skill I'm really using in this section is knowing where my root symbol is on my calculator. If you're not sure where to find the root symbol on your calculator, definitely send me an email, possibly a picture of the calculator. I'll see if I can find it. There's a ton of different calculators available to you, especially as web apps that definitely would have this ability. So for the first one, if I put in the root of 3, my calculator tells me that the answer to that is 1.73205. I am going to round this to 3 decimal places because that's what it asks you to usually in Cengage. The 3rd decimal place is 1, 2, 3 after the decimal, so I'm rounding to this number. I see that the number after it is 4 or less. That means I can just erase those digits without having to change the number. So my final answer here would be 1.732. When I go to do the root of 17, my calculator tells me that that equals 4.1231. Again, because this is 4 or less, I can just erase it and report my final answer is 4.123. When I go to do the root of 5 and then make it negative, I'm going to take a negative sign and then put it in front of my answer for root of 5, which was 2.2360. Again, that 0 is 4 or less, so I can drop it. When I put into my calculator 7, the root of 13, it gives me an answer of 25.2388. When I now look at the digit after the third decimal place, this is 5 or larger, which means I have to round up. So what used to be an 8 as my third decimal place goes up by 1 and becomes a 9 as I drop this fourth decimal place. So in each of the previous examples, I didn't have to round up because I was dropping something 4 or less. In this example, I did have to round up because I was dropping something 5 or more. When you go to do these bottom two problems, basically these are like things that we're going to see when we eventually do the quadratic formula. It's important to understand that there's an understood parentheses on top here. Before I can get to this division symbol, I need to do this subtraction or this addition. I would put it all into my calculator at once as parentheses 2 minus the root of 21 end parentheses divided by 2. When I put that in my calculator, I get negative 1.2912. Again, because this fourth digit is 4 or less, I can just drop it. When I now do it for the version where I'm adding the root of 21 on top of it, I get a value of 3.2912. Again, I can drop that 2 and just call it 3.291. So the key things to take away here are, do you know how to use this within your calculator and find the square root button, and then getting used to rounding to the proper number of decimal places. Now we're going to talk about simplifying roots of variable expressions. When n is even and x is greater than or equal to 0, we say that the radical, the nth root of x, represents an even root. We can find even roots of many quantities that contain variables, provided these variables represent positive numbers or 0. The reason they have to be positive, a positive times a positive, or a negative times a negative, gives me a positive answer. So to take an even numbered or square root of something, I must have a positive answer on the inside. There's no way to multiply something by itself and get a negative, because the only way to get a negative is a negative times a positive. So this is just reinforcing the idea that if we assume the variables are positive, we can take roots of variables. Find each root, assume that each variable represents a positive number. Really, what we're doing here is we're dividing the current power by the root number. Since these are all square roots, we're dividing by 2 because the root number is understood to be 2. So really, x squared under a square root becomes x to the power of 2 divided by 2, or x to the first. X to the fourth under a square root becomes x to the power of 4 divided by 2, or x to the power of 2. X to the fourth times y squared under the square root becomes x to the 4 over 2, or x to the second, y to the 2 over 2, or y to the first. So here are all those same answers. Root of x squared equals x, because x times itself equals x squared. Root of x to the fourth equals x squared, because x squared times itself equals x to the fourth. And finally, root of x to the fourth y squared equals x squared y, because x squared y times itself equals x to the fourth y to the second. These again are 4 or 6 problems that I'm going to show on the whiteboard to conclude this lesson. When I take the square root of a variable, as in each of these examples, really the key here is that because the square root is an understood second root, I'm just taking the power on the variable and dividing it by 2. So in part A, it becomes x to the 4 divided by 2. 4 divided by 2 is 2, so I get x to the second. In part B, I get x to the 20th divided by 2, which is x to the 10th. In part C, I get c to the 48 over 2, which is c to the 24th. In D, I'm going to split this up into 2 separate roots. First, the root of 16, then the root of x to the 6th. For the root of 16, I know that to be 4. For the root of x to the 6th, that becomes x to the 6 over 2. My final answer then becomes 4x to the 3rd. For 121, x to the 22nd, I can split it up into the root of 121, the root of x to the 22nd. The root of 121 is 11. I then get x to the 22nd over 2. So my final answer is 11x to the 11th. When I do part F, I get negative b to the 14 over 2, c to the 10 over 2. The negative stays. 14 over 2 gives me b to the 7th. 10 over 2 gives me c to the 5th. So my final answer is negative b to the 7th, c to the 5th.